Greetings, physicists. This will be a lecture on how to solve algebraically problems involving forces, mostly Newton's second law things. So, we'll be looking at F equals ma specifically. So let's start it off. We got a block being pulled by a rubber band, and we assume the rubber band is stretched to a constant length because the acceleration is constant. And it says there's a constant force. So we take that same rubber band, stretch it to the same length, produce the same force, but we attach to it a block whose mass we haven't measured. And we get a larger acceleration. So right away we can assume that this is going to be a block with a smaller mass. But we want to know what is that unknown mass. So let's write some givens. We have a block. It's 1.0 kilograms. Let's call that block 1, so we'll call that mass 1. And when we stretch on mass 1, we get an acceleration of 3.0 meter per second squared. So we'll call that acceleration 1. And when we do that on block 2, which mass we don't know, we get acceleration 2, I guess, of 5.0 meter per second squared. And that would be the acceleration of block 2. I think those are the only givens we have that we can use. And they say, what is mass 2? So our unknown over here, mass 2, what is that? We're looking for it. Now you can do this in 2 steps, or you can do it in 1. So I'm going to try and do it in 1 here by using a proportionality. And what we have here is that we're using the same equation no matter what. It's going to be sigma f equals ma, or sigma f over m equals a. Excuse me. Notice, however, that in both cases the force was the same. All right, that was actually stated in, hey there, don't move. That was stated in the problem. We have using the same force. So the sigma f in both cases, boy, it really wants to drag that. The sigma f in both cases is the same, so we could say, since there's only one force, it's the force of the rubber band, we could say that force 1 is equal to mass 1 times acceleration 1, but force 2 will be equal to mass 2 times acceleration 2, and force 1 is equal to force 2. So, what is that? That's either associative property or commutative property, and I always forget the two or confuse them. But by one of those two properties, we can say that mass 1, acceleration 1 is equal to mass 2, acceleration 2, like so. And now we just plug it in. We knew mass 1 was a kilogram, and acceleration 1 was 3 meters per second squared, 3.0 if we're keeping sig figs. Equal to mass 2 is our unknown. We'll leave it as mass 2. Oh, and I didn't solve this symbolically. Yes, mass 2 equals mass 1, acceleration 1 over acceleration 2. So we'll be dividing by acceleration 2. And acceleration 2 was 5 meters per second squared. And lo and behold, meters per second squared will cancel, leaving us with kilograms, which is what we wanted for a mass. So we're going to get 3/5. Or 0.6, so mass 2 will be equal to 0.60 kilograms. And notice, because everything had 2 sig figs, I'm keeping 2 sig figs. We don't count this guy. That 0 in front, he's just telling us how big we are. He's not actually a measured 0. Pretty easy? I think so. All right. Let's try another. If you watched the video on how to solve acceleration problems, you will recognize some of the statistics from this problem. We've got a jet plane, heavy jet plane, and it's going to take off of a runway, and they tell us how long it takes in terms of distance to take off, and it tells us the final speed of the plane. And it's saying now we're going to ask a force question, which is what is the thrust of each engine, of which it apparently has 2, pair of engines there. Okay. Well, let's write down some givens. I see a 51,000 kilograms, or 51 megagrams if you prefer. Love us some prefixes. 51,000 kilograms, and that is the mass of this plane. Plane and passengers and cargo and all together. Excuse me. Accelerates down the runway. It travels a distance. That's a 940 meters. That's a delta x. So delta x is 940 meters. Reaches its takeoff speed of 70 meters per second. So that's a v final of 70 meters per second. And this one does clarify at the beginning that it starts at rest. So we could say, or we will say, that v naught is 0 meters per second. The unknown here that we're looking for is the force. We want to know what is the force of each engine. Okay. Well, where to start here? Let's do this. We need an equation, and I think I'm actually going to need 2 equations for this, because if we try to do an F equals ma, which we will definitely have to use F equals ma, if we try to do F equals ma, you'll notice that we do not have acceleration, and we're looking for a force, so this would have 2 unknowns. So we need a way to get acceleration, but glory be, these 3 givens here do show up in our constant acceleration equation. So don't forget last chapter, you've got to carry all your chapters with you when you're learning physics. So if I'm doing that, it looks like this equation, v final squared equal to v naught squared plus 2a delta x. And that will work. So let's solve those up. The force equation, force is my unknown, he's already isolated, so I'm okay there, but I do have to isolate my acceleration variable. So I will get v squared minus v naught squared over 2 delta x. And I can go ahead and sub that in to my force equation. I can just put that right in for a and just have to deal with one equation, as long as that's not too onerous. You could solve them in 2 equations if you want. That's not going to hurt you at all. F equals m, and instead of a, it's going to be, so let's do parentheses here, v squared minus v naught squared over 2 delta x. And on bottom, I will, oh, no, I think that's it. All right, I'm getting ahead of myself. Now that I've got it all solved, I can substitute in. My starting velocity was rest, so that goes away. Makes this a little easier. Mass of the plane was 51,000 kilograms. And the velocity final was 70. So if I square that, that should be 1,400. And that's going to be meters squared per seconds squared. Multiply those. Divide by 2 times the distance was 940 meters. Everything looks good. Okay. There's not a lot to cancel here. I think this is just going to wind up going in the calculator. I will get meters canceled once. So I will get kilogram meter per second squared, or newtons, which is what I'm looking for. So let's do 51,000 times 1,400 divided by 2 times 940. And my calculator gives, it's a very big number, as you might expect from a jet engine. We get 3,797.8, etc. There's a lot of numbers in there, a lot of digits, sorry. Newtons. Now, if I am being a stickler for sig figs, I think we have 2 sig figs, so appropriate rounding is right about there, 38,000 newtons, or 38 kilonewtons. You could also write it like this, a lowercase k. Lots and lots of force, 38,000 newtons of force. Okay. Divide that by 10, and you get about almost a 4,000 kilogram object. So this plane is pushing hard enough to lift a 4,000 kilogram object vertically, which is no slouch. That's like lifting a couple elephants. Oh, and there's one thing where we still have to do. Haha, I almost forgot. And you might have missed this too, but if you go back to the problem, remember at the beginning we said this plane has a pair of jet engines, but the question says what is the thrust of each engine? So to get the acceleration, that force that we just calculated, that's the force pushing the plane down the runway, but that's divided amongst two engines, so you're going to have half it. So this is, each engine is actually putting out 19,000 newtons worth of force. So if you're an airplane designer and you are getting to gigantic forces that you are required to lift this plane with, and you can't quite hit it with the current engine technology, just make more engines. Although, of course, they have their own weight and stuff, so it's not quite that simple, but yeah. All right, moving on. Got a third one here. It's got a graph. Love problems with graphs. This is about seafood here. We've got some mollusk here. A scallop is gonna push itself along with this this water siphon that it uses and shoot itself backwards. Yeah, we have its mass. We know there's a predator coming for it, and we have a graph of its motion. We have a graph of how fast it was going at different times. And it says, how does this force compare to the weight? So we have two questions here. We're looking for the force itself, and we are looking for a comparison between that force and the weight of the scallop. So let's look at this graph. What can we get from this graph? I'm going to look immediately at the axes. What have I got on my axes? Almost always the most important thing you can find from a graph. And in this case, we have a velocity versus time graph. We've seen those before. Now, recall also that force, we're probably going to be using this almost every time we do a force problem. It's F equals ma. That's acceleration. So now you got to ask yourself, well, how did I get acceleration from a velocity graph? Well, acceleration is a change in velocity over a change in time, a delta v over a delta t. Well, on that graph, that's a delta, it's a delta y over a delta x. So that's just the slope of this graph. So k, the slope of this graph, will equal this, will equal acceleration. Good stuff. And we have a mass, so we will have that m. So I'm going to go ahead and put that here. M of the scallop is 25 grams. And if I want newtons, which I probably will because we're comparing it to newtons at the end, I'm going to have to change that to 0.025 kilograms, because kilograms and newtons go together. Those are the units we like for newtons. Okay. Don't do that. Here we go. So I need the slope of this graph, and whoever made this graph made it easy for us. If you can see, the bottom axis is kind of jumbled, but that's 0.1, 0.2, 0.3, and the vertical axis is 0.1, 0.2, 0.3, and this is exactly a 45-degree angle line. So the slope of this graph is 1. So the acceleration is 1 meter per second squared. Hallelujah. So my force that I'm going to try and find is equal to the mass times the acceleration, or 0.025 kilograms times 1 meter per second squared. And of course, 1 times anything is just the same. So 0.025 kilogram meter per second squared, which of course is a newton. So this scallop is accelerating itself away from the predator coming to eat it with a force of 0.025 newtons. So that answers the first question. Second question. How does this force compare to the 0.25 newton weight of the scallop? How does it compare? 0.25 newtons. Well, if you want, go ahead and divide it, but you can see that's a pretty easy times 10 ratio. So this force is 1/10 of this force, or basically it's pushing itself away with a force equal to 1/10 of its body weight. And weight is appropriate here, not mass, because newtons measure weight. Kilograms measure mass. So this is perfectly acceptable to say. Good deal. 1 to 10 ratio. On we go. Another graph. Love us some graphs. Oops. Here, move that guy over. Here's a graph of an object's acceleration versus force. What is the mass? Looks like it should be straightforward. Now, there are a couple ways to solve this. You can look at the graph and just pull givens off of it and get the answer to it. But I'm going to try a different way. First of all, what I'm interested in right away, what are my axes? I've got force on this axis, and I've got acceleration on this axis. I want to try and do this using a slope. What would a slope be? A slope is a delta y over a delta x, which in this case would be an acceleration, delta acceleration, over a force. Acceleration over force. Let's look at that. F equals ma. What would acceleration over force be? Well, acceleration over force, if I rearrange this, if I divide by F, I would get 1 equal to m times a over f. And if I want to isolate the a over f, I could divide by m and get 1 over m equals acceleration over force. So acceleration over force is the inverse of mass. So I can't just take the slope of this graph here, because that would give me not the object's mass, but its inverse. So there's many ways you could approach this. One way would be, instead of doing delta y over delta x, you could do delta x over delta y. That would be the inverse of the slope. That's fine. You could do, instead, lost my train of thought. Essentially, I'm gonna go ahead and do a version of this. I'm gonna take the slope initially. I'm gonna take this, the a over f, which, if we look at the graph, the a does go through the origin and winds up at 4. I need to actually recenter this because I've dragged the picture. There we go. So the a does go through 4 and 0, so I can do, and it goes from 0 and 1. So essentially the slope of this line is 4. It's going to be 4 over 1. And let's go down here and do that. So I'm going to get 4 meters per second squared over 1 kilogram is my slope. But I don't want the slope, I want the inverse of the slope. So if I get an answer of 4, I'm going to take that and go 1 over 4. And 1 over 4 is just 0.25, 0.25. And then I flip it, and so I will get kilograms on top and meter per second squared on bottom. Let me make sure I'm not messing that up. I am messing that up. It shouldn't be kilograms. It should be newtons. And of course, a newton is a kilogram meter per second squared. Come on. There we go, pen. So when I do this, my meter second squareds will cancel, and I will get kilograms only. So 0.25 kilograms. Let's see if that answer makes sense, because I did a lot of hand waving there. Here is a graph of an object's acceleration. So they didn't even tell us what the object is. So yes, without knowing any context, we can easily say this looks like a quarter of a kilogram object. Should make sense. All right, that's that graph. One more. Crash tests. Okay, driving a car into a wall. Fast. Well, actually, that's 35 miles per hour. That's not meters per second. So below is the acceleration versus time graph. Let's actually make that an acceleration versus time graph, because there should be some drawings on there. Here we go. Here's the actual drawing of this right about here. We hit 300. Okay. So this is a car as it crashes into a wall. We'll say that 0 looks about like the time where it hits, and then maybe around 200 milliseconds is where it comes to rest. So we have the graph, and they are asking, what is the maximum force experienced by this car? We have the mass of the car. Again, axes matter. This is an acceleration versus time graph. Well, unlike a velocity versus time graph, if this was velocity versus time, I would definitely have to solve for the acceleration. I don't have to do that here. This is an acceleration versus time graph. If I'm trying to get the force, remember force is F equals ma, the maximum force, well, the maximum force would come from the maximum acceleration because the mass will probably be constant. I mean, maybe the car falls apart after the crash, but it doesn't say anything about that. So all I need is the biggest acceleration possible during this interval, and that's going to correspond with the biggest force. Where's the biggest acceleration? Right there. So this is a little easier than maybe the graph makes it look if you didn't look at the axes, if you panicked and tried to do this quickly. So go ahead and say A, we'll just pull that out as a given. The max acceleration, A max, equals 300 meters per second squared. Time here doesn't matter. Not a variable we're interested in. It just tells us that it occurred at around 75 milliseconds, but that doesn't really factor in. So let's plug this in. We also have the mass. Sorry, let me write that real quick. The mass of the car is 1650 kilograms, which they gave us. So I have acceleration, I have mass, and I have my equation. I'm going to be looking for mass, so let me solve for mass. The mass, oh nope, I'm going to be looking for force. Never mind, force is already isolated, so force should equal those 1650 kilograms times those 300 meters per second squared. And kilograms and meter per second squared are good units to use for force, so no conversion necessary. Let's plug this sucker in. 1650 times 300, and I'm getting, oh boy, 495,000, excuse me. Here we go. 495,000. And according to the numbers they give me, this looks like a measured value, so, and 300 could definitely have 3 sig figs. So I'm okay not rounding this past the 5. This is totally okay, and then these zeros trailing it don't necessarily have to be significant, so we're okay there. That is plenty of rounding. 495,000, and it is in newtons. Good deal. I like these problems. There are plenty of graphs in there, and hopefully this will help you with your solving your force problems.